Now we continue to discuss what we had started doing last time, namely the open string. Okay, if you remember, we had this open string which had sigma going from 0 to pi, and we allowed ourselves to put degrees of freedom at the ends of the string. These degrees of freedom, the degrees of freedom we allowed ourselves at this point were the utterly trivial ones, the ones in which which do nothing. Okay, they're just some vector space, some n-dimensional vector space here. The basis vectors are labeled by I runs from 1 to n. Okay, similarly here, j runs from 1 to n. These things were called Chern pattern factors. Okay, because they're doing absolutely nothing. As the string evolves, if you start with an I here, you end with an I here. Nothing happens. Similarly with the j. Then nothing happening becomes more interesting when we look at string scattering amplitudes. Right? Nothing happening means that the I index along any line is not changed. But the I index here and the j index here need not be the same. The j index along this line is not changed, and so on. So now, when we look at the scattering of an open string, we have to specify its state, not just by what its oscillators are doing, but also by what the Chern pattern factors are doing. Okay? So we specify this by some matrix, such that lambda ij tells you that the Chern pattern factors are lambda I, Chern pattern I, Chern pattern j. Okay, so this is the state in the Chern pattern space specified by a matrix lambda ij. Is that clear? And as we discussed in the last class, we had, suppose we had lambda 1 here, lambda 2 here, lambda 3 here, and lambda 4 here. Then the full dependence on lambda, because of this structure, is trace lambda 1, lambda 2, lambda 3, lambda 4. Is this clear? Any confusions about this? So adding the Chern pattern factors effectively just adds this factor of trace lambda 1, lambda 2, lambda 3, lambda 4 to what would have happened had you had no Chern pattern factors. It's no problem. Go ahead. Okay? Now we want to do some sample calculations illustrating this point. Yeah, and trying to understand how we can compute open string scattering amplitudes along with these Chern pattern factors. Okay, so let's first do the simplest guy. That is the scattering of two tachyons with the gauge field. Okay, now let me just once and for all write down various correlation functions that keep coming up, so we don't get confused with factors of 2. The rule on the boundary, there are extra factors of 2 as we discussed last time from the boundary and the bulk. So we cleared that up last time, and I'm just writing down the answer so we don't keep having to worry about this. If you have a product of e to the power I k dot x, ki times x of sigma I, and you have all of these, and these are all these are now on the boundary. Okay, so these are boundary ordered. I think Pulchinski calls them something. That's a funny name like this. Okay, but this is of course y sigma ij. I think Pulchinski calls these yi's. Let's follow. So he calls them it's yij to the power, and then the factor of 2 is important. So we get yij mod to the power 2 alpha prime ki dot kj. Product over I not equal. Okay, and similarly, when we want the expectation values of the form del xi e to the power I k dot x at sigma I. E to the power I k at sigma I, yeah. So let's remember what the rule was when we had these open strings. Firstly, what we did was to replace this by an effective del x oscillator, and then there was an explicit factor, right? So there is some del yi, some effective oscillator, which just has to be contracted according to Wick's theorem, and then there are the plus additional factors. Now the additional factors were of the general form ki divided by y minus yi, right? So this guy is at some y, then it could contract with all the other exponentials. Okay, so every factor of this effectively is replaced by del yi plus, and now the important thing again is the things that change are the factors of 2. So there's minus 2i alpha, then kj, because you're contracting this with an e to the pi kj, over y minus sigma j sum over j. Let me see if I've got this right. K, yeah. Okay, the guy we've got is at y, sigma is sigma j, and then k, sorry, let's put this as mu and j. Now this is correct. Okay, do you understand what this rule means? It means every time we've got a contraction with the del xi, that contraction is replaced by a formal oscillator. Del, let's call this mu, sorry. So del y mu, which has no contractions with the exponentials anymore. Only contracts with itself, according to Wick's theorem. The contractions of the exponentials we've explicitly taken care of. This comes from the contractions of the del x's with all the other exponentials in the game. Doesn't contract with its own exponential because it was normal ordered. It contracts with all the other exponentials. So every other exponential that appears gives a factor. The effective factor was 1 over y minus sigma j, where sigma j was the location of the other exponential. Okay, then kj, that was the momentum in the other exponential, and the mu index here is kj mu, and there's the 2 alpha. If you remember, we derived this very carefully for the closed string. There's a similar rule for the open string, and this is just a matter of getting the factors of 2 correct.
So now also we have to consider boundary operator as 2 mirror operators and take del x with this.
Exactly. So once again, we just take the boundary operator as the limit approaching the boundary, and just do all the contractions, exactly as we did last time. Apart from the self-contractions, and that basically removing those self-contractions, including the self-contraction with the mirror, requires you to change what you mean by normal ordering, right? So exactly in what the same logic as what we did, as we implemented last time. It's the same thing. It gives something very similar to what we had for the closed strings, just with some extra factors of 2. Because the extra factors are 2 because there are 2 operators. Oh, it's alpha by 2 and now it's 2. Actually, I don't even remember that, but that's probably because you see all of these operators are boundary operators, right? Okay, so you could have a contraction like this, like this, like this, like this. Right? So just check it carefully. But yeah. 4 contractions. Okay. So now we're going to use these rules in order to do the calculations we want to do. So let's first do the calculation for 2 tachyons and a gauge boson. Okay. So the rule for the 2 tachyons and a gauge boson. So suppose the first tachyon is at sigma 1, so that's a T. Second tachyon is at sigma 2, and that's a T. And the third tachyon is at sigma 3. Okay. Sigma 3, and that is a gauge boson. Okay, actually first, before doing anything else, let's do 3 tachyons. We did this last class. I'll just remind you. So there were just 3 tachyons. Okay? Now, the answer to this is what? Well, firstly, from the C ghosts, we get a factor of sigma 1, 2. Let's call these y's, like which is y1, y2, y3. So we get a factor of y1, 2, y2, 3, y1, 3. This is from the C ghosts. And then we get an e to the power I. Then we get from that rule, from this rule here, we get y1, 2 to the power 2 alpha. What is alpha? This is really,
alpha prime.
that was an alpha prime, right? Not an alpha. What did I do? Yeah, 2 alpha prime. Yeah, that's an alpha prime. So 2 alpha prime k1 dot k2, and similarly for the y13, 2 alpha prime k1 dot k3, and so on. Okay, and now let's remember how these k1 dot k2 factors go. K1 dot k2 was equal to k1 plus k2, the whole thing squared, minus k1 squared minus k2 squared divided by 2. And what was the mass of this tachyon? In the closed string we had 4 by alpha prime. Here I think it's just 1 by alpha prime, right? Right. So this thing is 1 by alpha prime, but with a minus sign because it was tachyonic. No, but k squared is minus m squared. So this is with a plus sign. A minus 1 by alpha prime minus 1 by alpha prime, the whole divided by 2. Okay, so this is equal to half minus half by alpha prime. Okay, so this whole thing here is y12 to the power minus 1, which cancels the y12 here. Similarly, the y13 to the power minus 1, which cancels the y13, and so on. So this was just a number. Okay, had we had no pattern factors, the number would have, the answer for the scattering amplitude would have been 1, or more precisely 2. Right? Because there were 2 cyclical orderings for these points. Now with the Chan pattern factors, the origin of these 2 becomes clearer. Because one of the amplitudes, which is in this cyclical ordering, is just trace lambda 1, lambda 2, lambda 3. The other amplitude was trace lambda 1, lambda 3, lambda 2. When all these lambdas were just 1 cross 1 numbers, okay, this reduces to 2. But the reason that it was 2 is that there were 2 different trace structures. It becomes very clear now once you have the Chan pattern factors. Okay, so the 3-point function is just anti-commutator lambda 1, lambda 2, lambda 3 trace. That's the 3-point function of 3 tachyons. Is this clear? Excellent. Okay, now let's do another example. Now let's do an example which is 2 tachyons and a gauge boson. Okay, so 2 tachyons and a gauge boson. So let's say that we've got tachyon at y1, y2 and a mu at y3. Okay, so the only difference is that we have e to the pi k1 dot x1 of y1, e to the pi k2 dot x2 of y2, but then we've got del x at y3 mu times, and let's put an epsilon mu for the polarization of the photon, e to the power I k3 dot x3 at y3. And we've got the same ghost factors before. Okay, so what do we get? We get what we would have got had this not been there. So once again we get y12, y13, y23, this is from the ghosts. Then we get y12 to the factor 2 alpha prime to the power 2 alpha prime k1 dot k2, y13 to the power 2 alpha prime k1 dot k3, and y23 to the power 2 alpha prime k2 dot k3. We get these factors, but in addition we get what we would have got from this business. Now this doesn't contribute because that is a formal oscillator that has to Wick contract with something else, and there's only one object, so there's nothing for it to Wick contract with. Okay? So all that you get is from here. So let's understand what we get from here. What we get from here is the whole thing is multiplied by minus 2 alpha I and then k1 mu dot epsilon mu. K1 mu dot epsilon mu over y3 minus y1 plus epsilon mu k2 mu dot y3 minus y2. Okay, this is what we call y32. This is what we call y31. This is what we call y32. Is this clear? Okay, let's not get rid of those since we'll need them a lot in this lecture. Let's go back here. So now we just put things together. Okay. Right. So now we just put things together. First, we have to calculate each of these. So k1 dot k2 was k1 plus k2 the whole thing squared, which is 0, minus k1 squared minus k2 squared divided by 2.
Which is just minus k1 squared.
So k1 squared was
minus alpha.
plus 1 by alpha. So minus k1 squared is minus 1 by alpha prime. So we're going to get minus 2 by alpha prime because k1 squared.
No.
Minus 1 by alpha prime because half and then k1. Yeah. So we get again good. So we're going to get and that minus 1. This basically will just be left with a factor of 2 with a minus 2. Okay. So we've got y12 to the power minus 1.
Other 2 will be 0.
Because this has cancelled this.
Yeah.
Exactly. And the other 2 will be 0 because this is k2 squared minus k1 squared minus k3 squared. K3 squared was 0 and k2 squared minus k1 squared was 0. Okay. So we get y12 to the power minus 1, y13 to the power plus 1, y23 to the power plus 1, right? Because of the contribution from the ghosts. Okay, so we've dealt with all of this, all done. What remains is this stuff. Okay, now we need 2 alpha prime I with a minus sign. Okay, and then we have epsilon mu. Okay, now the first thing we're going to do, it looks like these numerators are different, but they're actually not. Why not?
Because of epsilon mu dot k mu k3.
Epsilon dot k3 is 0. Therefore, k1 is equal to minus k3 minus k2. But we can forget about the k3, so it's minus k2. Okay, so each of these can be replaced. This can be replaced by k1 minus k2 divided by 2. And this is k2 minus k1 divided by 2. And so this is epsilon dot k1 minus k2 by 2. Okay, this I'll call k12 times 1 by y31 minus 1 by y32. Okay, And then we will get now, so this becomes 1 by y32 minus 1 by y31, which was 1 by y12 up to some sign which we won't keep very careful track of, y12, y31, y32. And it's beautiful. This cancels. This had to happen, right? Because otherwise we're doing something wrong. Things can't depend on where we inserted things. So it's a test that it's working. And then what we're left with is this epsilon dot k12 divided by 2. So we've got up to minus alpha prime I, minus we won't worry about too much. Epsilon dot k12. Okay. Now, one thing we should be a bit careful about, anyway, in this case, epsilon dot k12 and this was for this ordering. But you see, where did the ordering matter? It didn't matter at all. All of this calculation didn't care about the ordering. Okay? We have to be a bit careful. Okay? See, the only place it might have mattered is if we made a mistake of a sign. Now, absolute signs we may not want to keep track of, but relative signs we must keep track of. Okay? So, in going from here to just cancelling this blitzly, okay, you have to be a bit careful about signs. Okay? In this case, it works out. It's just what we did. Okay? But this is the only possible thing to worry about. Possible relative signs. And I'll come to a place where, I'm not sure we'll do it in class, but I'll at least point out a place where these relative signs are sort of important. Okay? But in this case, you think about it carefully, every sign is what it is. Okay? And we just get trace of lambda 1, lambda 2, lambda 3, let's say anti-commutator just as before. Trace lambda 1, lambda 2, lambda 3. Lambda 1, lambda 2 was the anti-commutator. Okay. Now, this was the amplitude you got for 2 tachyon scattering with the gauge boson. Now, I'd like somebody to help me produce an action that would reproduce the scattering amplitude.
Young-Mills coupled with adjoint scalar.
Excellent. Young-Mills coupled with adjoint scalar. Excellent. Okay. So let's look at this. Oh, did we get the sign wrong? Was it? Let's look at what it should be.
Because otherwise, in abelian case, it should be 0.
Yeah. You're probably right. We probably got the sign. Just a minute. Let me just see what this. We may have to go back here and check the sign. Just 1 minute. But of course, what we want is T mu, as you said, del mu T mu plus A mu T mu. A mu T, the whole thing square. Trace of this. Okay? And now, yeah, I think we have to go back and check this sign. Sorry, I asserted very confidently that the sign was right. It's wrong. But let's see what we expect from the Lagrangian. And Upmanyu's argument is a good one. We should have got 0 in the abelian case. This is not 0. Okay, but let's expand this out. So we're going to get 2 terms. Okay, both of which are basically del mu T, A mu commutator T. Trace. Okay. Now, what will this amount to? Let's say this was particle 1, this was particle 2, this was particle 3. This would amount to K1 mu epsilon mu. Trace. Now, lambda 1 commutator lambda 2 lambda 3. But because of cyclicity, it doesn't matter where you put the commutator. It's the same as trace of commutator lambda 1 lambda 2 lambda 3. And here we've got K1 mu epsilon mu, But we've seen before that k1 mu can be replaced with k1 2 by 2, because k1 mu. So we've got the same amplitude, except we've got an anti-commutator. Okay, so we've made a mistake here. We've just not been careful enough about sign, so let's go back and fix the sign.
What if we replace 1 and 2? Then the total sign should be same.
The total sign should change.
Including the trace part.
Including the trace part.
No, there's no, I mean, at first,
Yeah.
Yeah.
Let's just do this carefully. Okay. So let's see. So this part was okay. So now this part, of course, was fine.
Yeah, no, I think even that was okay, but after you introduce lambda 1 and lambda 2, if you interchange 1 and 2, the k1 2 has to be, there has to be a relative sign between the two which will make it an anti.
That's probably right. That's probably right. So let's go back here. What we had here was k1 2, 1 2 dot epsilon. That was okay.
Yeah.
Then we had 1 over y
And
3 1
there was over 2 there, but that's
minus 1 over y 3 2. Yeah, that was important. Okay, now it's sort of clear. The important thing is now we do this carefully. This is k1 2 dot epsilon. And then we get 1 over y 1 2 over y 3 1 y 3 2. Now this is what you were saying. This term is symmetric under interchange of 1 and 2. So we go from one ordering to the other by interchanging 1 and 2. This term is symmetric under interchange of 1 and 2. But this term is antisymmetric.
But then k12 is.
but this,
K1 2
So
is
both
all
of them
I think
at the
this
same.
only that one,
Yeah.
k1 2 is probably.
good point. K1 2 is also
So
antisymmetric.
k12 and y12 is making it positive. Everything.
Right. Give me a minute.
If y1 cancels, then
We don't want that answer, right? We want to see that it's the
Then lambda 1, lambda 2 should give some negative sign.
no, lambda 1, lambda 2 is whatever it is. There's a term which is trace, lambda 1, lambda 2, lambda 3.
yeah. And the other term will be
What?
Ordering.
minus lambda 2 lambda
The
1.
other term is trace, the other order. The signs have to come from the rest of it, right?
Yeah. I mean, it should just be k1 2. I think.
What do you mean?
Just from k1 2, I mean, if the y1 2 is cancelled as before, just from k1 to this will come because.
But then we have to understand why we're allowed to cancel K1.
Yeah.
Right, just a minute. Let's think about this and let's think about the ordering carefully. Let's think about what fixes the signs. Firstly, here were we careful? Probably not, right? Let's be careful. What was mod? The thing that came from the C's was a mod. The thing that came from the exponents was not a mod.
Right.
Let's be careful. Let's be really careful. Let's do it. When it's an issue of signs, we have to be very careful. Minus 2i alpha prime. That's y1 2, y1 3, y2 3. Then we got this extra factor of y1 2 down here square.
Yeah.
Since it was a square, it didn't do anything. It's not changed anything. Okay. Okay, let's keep being careful. Okay.
The final answer is coming out to be epsilon dot k12, right? There itself you have a sign.
But what about the extra signs in the y12s? We just have to be very careful that we understand every sign. This is the trickiest thing in the game, right? I mean, it's true. If we ignore signs from the y12, it's working. That's what. But what's the rationale for that? Just now. Let's be as careful as we can. Let's see. When we did, let's see what every sign in the game is. What is the rule? You see, we should go around in cyclical ordering. That's probably the point. You see, suppose we do. Here, we've got 3, 2, and 1. but it's making no difference, right? We're going down this way, 2 and 1, but it didn't matter what ordering for this. And 1, if we interchanged it at 1 and 2, we also got the same thing. We also got the same thing, right? Just where's the sign? Just, where is the cyclical ordering mattering at all? Just one. Wait, so the question is, are these y12s or are they mod y12? No, they are y12s.
Is it because C's?
But somebody has a solution?
Is it because of the C's? The interchange C's also.
Oh, this is a good point. This is a good point. This is a good point. This might be it. This might be it. This might be it. This might be it. Yeah, let us remember what was the two? I think you're right. What was the two?
That would be the case in 3 tachyon scattering as well.
That's also a good point. Let's think for a moment. Let's think. What was the logic? So how did the C's come? We have a No, I don't think it's a C's, because of the following. What we had was contraction of 3 C's and contraction of 3 C bars. You see, think of it from the bulk. There was like mod Z squared, right? I think that I think it's just gone away. Just give me one more minute. Give me one moment. Well, let's see if Pulchesky says something about this. Where does he work this out? Where is it? Give me one more. Sorry, people. I think I think probably the way to think of it is, as you say, it's probably. I think sorry. I think I was just confusing you guys. Let's do this. This is absolutely, as we say, this is absolutely right, and this part of it. Sorry. No, what am I? I'm confused. But maybe it is the C's. Just a minute. I mean, the question is, what part of this calculation, what part of this correlation function calculation depends on cyclic order at all? Right, there's the part with the lambdas and there's the part with the oscillators. And naively, the part with the oscillators is totally insensitive to the cyclical ordering. That's what's confusing, right? So it naively looks like we are getting just two different things that are the same, but of course there's some subtlety in that. For instance, when I say the point is this, right? When I say y minus sigma, this has an orientation associated with it. What does y minus sigma mean? In which direction? Right? This y minus sigma, if we were on the disk, if we went this way, we'd get one number. If we went this way, we'd get another number. Which way is y measured? Is it measured that way or this way? Okay. So clearly there is some issue with this business, and how did that actually happen? How did we get so the question is, how did we get a 1 over y minus sigma in our calculation? Right? Let's take a minute to figure that out. Okay, let's take a minute to derive this formula. Okay, and that will help us. Yeah, it better be a y minus sigma, because otherwise we're not going to get y12 here. Mod minus mod won't give us mod, right? So it's really is a y minus sigma. It's not a mod. Let's try to understand how that formula is coming about. Okay, so the thing that we want to do is to understand what happens when we do del x e to the pi k, let's say del x y3 e to the pi k 2x of y2 e to the pi k1 x of y1. The other k is not important, so we forget about it. Okay, so this is the thing that we want to try to compute. Now let's try to understand exactly what this means. So we're on the half plane, and we're going to use the same general method as before. Because we're in the half plane, we're going to use the doubling trick. So this was a del x here, and it's going to approach the real axis. Similarly, there's another del x here, which is going to approach the real axis. We're not going to allow ourselves to contract the del x's with each other, but we will allow contraction with all these other guys. So this guy will have an e to the pi k1 x of y1. This guy has e to the pi k1 x of y1, and it's now a 6-point function, because we've got 2 del x's, 2 e to the pi k1s, and so on. And this is an e to the pi k2 x of y2. This is e to the pi k2 x of y2. This one's a little bit above, this one's a little bit below, and we take the limit. Okay, now since we're never going to contract this with this because of normal ordering, we can just put a factor of 2 here. Similarly, we can put a factor of 2 here. Okay, so effectively we have del x of x.
It's a 4 because the lower one also contract with both of these. I mean, so when each of the contraction, for example, if del x at y3 is contracted with the one at y1, there will be an effective factor of 4 because
del x at y3 at this one?
Yeah, y1 and y3
yeah.
will effectively have a factor of 4.
But that's because there are 2 del x's.
Right.
But I'm saying just this operator becomes e to the power 2i.
Right. Okay.
Right?
Yeah.
Right, so there's going to be a del x, there's going to be another del x at x.
Yeah.
There'll be 2 of these. And we're not going to allow ourselves to contract. Fine. And then we've got e to the pi k dot 2k dot x of y1 and e to the pi 2i k2 dot x x at y2. Okay, we want to compute this correlation function. Now we're interested in the terms in which we've got contraction of this guy with this guy, for instance, right? So and we're working completely holomorphically now. Now everything is just purely holomorphic, right? So that's why it's the fact that we've got this del x contracted to the e to the pi kz and it's purely holomorphic that is giving us 1 by z. It's giving us 1 by z, and therefore that 1 by z was becoming the 1 by y. That had a sign. By the way, we're going to get two of these contractions. Yeah, this. Sorry, people. Sorry for this. It's not even right. It's not even right that, sorry, I'm saying all kinds of wrong things. Firstly, I said that this guy should be thought of as this del x and this del x. That's wrong, right? It's not. This is really just a boundary operator. Yeah, it's not like this quadratic in epsilons. It's just 1 del x. It's 1 del x here. Sorry, this is just 1 del x here. But just 1 minute more. But now the main point is that this is now a completely holomorphic thing. So we're going to get 1 over x minus y1, 1 over x minus y2. Now, the thing is, let's suppose this guy had been on the other side. We would get the x minus y1 that way, right? Should really do the calculation genuinely on the disk. Okay, I'll tell you what. I'll try to clear this up and come back. I'm sorry about this. There's a minus sign that I'm not getting straight here. There should be the minus sign, as Upmanyu pointed out. There should be the minus sign from sanity. but it's a subtle minus sign. I know I've once understood it. I mean, I've many times understood, but I cannot remember it. Okay, I will get this straight and give you a proper justification. Pulchinski, of course, just keeps quiet about it.
What was the, so you said, what is the Lagrangian which will reproduce this particular answer?
Yes.
And how was it that it's Young's with
If you allow me to put the minus sign.
yeah.
If you allow me to put the minus sign, this is just d mu t, d mu t, d mu t. Suppose you take d mu t, d mu t. Trace of this. Okay. Now let's take the function that was the 3-point function between two tachyons and a gauge boson. So one term, let's say we take the derivative from the first guy and the commutator from the second guy. So this is this object. Now, let's say this was particle 1, this was particle 2, this was let's say call this particle 3, this is particle 2. So this is k1 dot epsilon. Okay, and then we will get trace of lambda 1, lambda 3, lambda 2 minus trace of lambda 1, lambda 2, lambda 3. Now cyclically permute the lambda 2 here. So this is equal to k1 dot epsilon into trace of lambda 1 commutator lambda 2 lambda 3, which is that. K1 and K12 makes no difference, right? Because momentum conservation. Okay, so no, we clearly need the commutator. We clearly need the commutator. There is a relative minus sign. This is the most subtle thing in computing these things. These are relative minus signs, and we have to get the rules straight for that.
So the answer we were supposed to get was of two tachyons and one gauge boson was 0, is it?
No, it was this.
Okay.
It was we were supposed to get what comes from a space-time Lagrangian, right? This is what comes from the space-time Lagrangian. We're getting exactly the same thing, except we are naively getting with an anti-commutator.
Yeah.
The answer comes here with a lambda 1 commutator lambda 2. We're finding lambda 1 anti-commutator lambda 2. Okay? We're finding the same two terms, but with the wrong relative sign.
And that is 0.
What?
That is 0.
Not 0. It's what it is.
No, I mean anti-commutator will.
No, it's whatever it is.
It will be 0 in the space.
K1
The
is
answer we
implicit
got
by K1
was epsilon 1 2 and commutator of 1 2, anti-commutator of 1 2. That will be 0. What we are getting is
K1 to epsilon.
No, in general, none of them are 0. And neither the commutator nor the anti-commutator.
no. I'm saying what the answer we have got right now. The wrong answer is
Ah.
turning out to be 0.
The wrong answer is 0.
You're saying once we symmetrize over 1, 2, 3.
Yeah.
Once we symmetrize over 1, 2, 3, you're saying that we would get, we would manifestly get 0. That's correct.
Just 1 to symmetrization with.
Correct. This I agree. We're getting something totally wrong. Yeah, we're getting something completely crazily wrong. And yeah, you're saying we're not getting an answer that is invariant on 1 goes to 2. So surely that must be the answer.
That's why commutator is necessary.
Necessary. You're absolutely right. And so now you could ask, okay, very good, very good, very good. So you could ask, okay, if I interchange 1 and 2, I should get absolutely the interchanged answer. But when I actually do the calculation, I'm not getting the interchanged answer. Okay, so it's a very stupid mistake you're saying. So let's see, this should be able to help us fix it. Thank you, good point. Yeah, okay, fine. So this must help us fix it. Let's do it again. What did we get? We got y12, y13, y23 mod. Then we got y12, the whole thing square. And then we got k1 dot epsilon over y12 y31 minus k plus k2 dot epsilon over y32. And you say at this stage it's obviously invariant
Yes.
under k1 to k2.
Yes.
So, okay, it's stupider than I thought. Thank you, people. Thank you. Okay. Now, let us take this and now what I did was I wrote this as k12 dot epsilon, some factor of half which I don't care about, over y1 over y31 minus 1 over y32. Okay, and then I made this y.
No, but even at even at this stage there will be a trace factor. Let us write the trace factor here.
Right.
And, without the trace factor there was no.
This is
Yeah.
already.
Yeah, this was all.
No, but this is one term though.
No, this was even before, even previously this was what was there.
I agree. But we're going to add two terms. That's when the trace factor will become important. Right? I mean, and this was y12, let's say. So this is what we got.
Yeah.
And you say the problem is that this term is symmetric.
This is the.
That's why.
And therefore, if we add symmetric, so you know what you're saying is that the problem is that the y12 dependence is not cancelling. This is what you're saying. Okay, you've narrowed it down. You see, for the amplitude to be proper, it should not depend on.
Oh, hi, Shiraz.
Uh-huh.
So you will bring the speaker downstairs?
Sure, I'll bring the speaker downstairs.
It is in 10 minutes.
In 10 minutes, okay, I'll come down in 10 minutes, yes. Okay, thanks. Huh. Right, so you've narrowed down the problem to this.
Also introducing this.
Okay, I'll introduce it. Yeah. So you've narrowed down the problem to this. What you're pointing out is that actually the y12 dependence is not quite cancelling. It's cancelling only up to sign.
Yes.
That's the problem. Because
I mean that square, replacing that square by the first combination of y12 by mod of y12 to the power minus 1 is not correct.
yeah. So the problem was, were this to really cancel, then this would manifestly be antisymmetric.
Yeah.
Yeah.
And
There's an additional sign.
the additional sign.
I
So
mean,
what?
additional mod.
Yeah. What is the logic for that? Exactly. It's just that had this been mod y12, everyone would have been happy. And the question is, what is the logic for that? Let me think it through. I'll give you a proper answer by the next class. So it's a subtle point which we have to get straight. I'll try to get it straight. I wonder if. Yeah. Okay, let me think it through and okay, so I owe you an explanation for this sign, which I will give you by next class. I wonder if the next calculation will have the same issue or not.
It's always better in close please.
Exactly. Okay, the next calculation I wanted to do. Was to do 3 gauge boson scattering. But this is one of those calculations that is actually easier on the easier on the superstring than the bosonic string. So let's do it in the superstring. I wonder if we'll see the same issue here. Maybe not. Let's see. Okay, let's see. Let's see. Okay, so both for variety, because we shouldn't get used to doing only bosonic calculations, as well as because it's the easier calculation, we're going to now work this out in the closed string. So let's remind ourselves. Now, everything we said about open strings carries over to the superstring theory. Okay, everything we said about open strings carries over to superstring theory. Once again, there are Chan-Payton factors. And now what we're going to do is to compute the 3-gauge boson scattering in type 1 theory. So the theory which has open strings but is super. We'll come back in a couple of lectures to exactly understanding what type 1 theory means.
These are open unoriented strings.
Open unoriented strings at the moment. We'll come back in a little while to understand when that is okay and so on. We'll have to do one loop amplitudes for that. Okay, we'll understand that. Exactly. So we'll come back to discussing this. But right now, let's not worry too much about it. We're just going to do scattering amplitudes for open strings in the superstring. So what do we have to do? Well, we need 3-gauge boson operators. But remember, there was this new issue in the superstring. The new issue with the superstring was that all your gauge boson operators could not be in the -1 picture. Right? In fact, we were allowed to have 2 gauge boson operators in the -1 picture, but the third one had to be in the 0 picture. And remember, when we discussed all of this, we carefully worked out what the vertex operator was for the gauge boson. For the gauge boson in the -1 picture, of course, was e to the power -5 psi mu. That was the gauge boson in the -1 picture. Okay, but the gauge boson in the 0 picture didn't have the e to the power -5. That's why it was in the 0 picture, and looked much more like the vertex operator. Okay, vertex operator in the. Okay, so let's put this at sigma 1 or y1. 1 e to the power -5 y2 sine nu at y2. So let's say that this is dotted with epsilon 1 mu. This is dotted with epsilon 2 nu. And then there is the more complicated guy, which was I x rho dot. Dot was in the direction along the boundary. Okay. Plus 2 alpha prime k3 dot psi into psi rho. Psi rho epsilon 3 rho. Okay, so this is the correlation function we have to compute if we want to compute expectation values in I wonder if in the end the answer, sorry about the previous question, I wonder if in the end the answer is going to be, I have to think it through. I will and I'll give you a proper answer. But I wonder if in the end the answer is going to be what Sunil suggested. That the C goes to C12, C1, Y12, Y13, Y23. Then for the tachyons, we got divided by Y12, Y13, Y23.
Actually, you said that there are C bars also, but in the open string.
There's only a C. There's only a C. There's only a C. Yeah, right. I said it wrong. Maybe his answer is right. Yeah, I was thinking of it as a limit from the bulk, but it's not right. It's not like there are 2 C's, because there's only one. There's only one C, right? So you're right. I said that wrong. So maybe this is the answer. The reason that there was no sign with the with the tachyon is that the integrand for the tachyon also had its own sign. Right, because we had those e to the pi k dot odd factors, and that was a signed quantity. There was no mod there. So there it cancelled. Whereas here for the gauge boson, this y12, y13, y23 only came with the y23 square. Let's say a y12 square. So this integrand for the gauge boson is not picking up a sign under 1 goes to 2 interchange, whereas this guy is. Whereas in this case, both picked up the sign. And so they cancel. I think this is likely in the end to be the answer. But of course, we have to put it in terms of a proper framework, make sure we understand it well. I'll give you a proper answer next time. I think that is potentially what is going on. But I'll come back to that. Okay, yeah, right. So let's go on. So what are we going to get here? Firstly, we'll get from the C ghosts, y12, y13, y23. We get this factor, that's as usual. Then we get the contraction from the two e to the power 5s. That was effectively a 1 over y12. This you remember from our study of that ghost, that bosonized ghost. So we got a 1 over y12. And then what we get is whatever we get by contracting either this with these or this with these. Okay? So we're going to get two kinds of terms. Let's look at what we get by contracting this with these. If we do that, the size will contract with themselves. So that will give us effectively an epsilon 1 dot epsilon 2, because psi mu, right? And psi contracted to give us an effectively 1 by y12. Okay, so this contraction we've dealt with, and then we have to also do this contraction. That is and there's the e to the pi k's. I've not written that, but each of these has its own e to the pi k factors. So now we need to do the contraction of this guy with these two. That's exactly the same factor that we looked at for the tachyon contraction. Okay, so that will give us this factor of k12 dot epsilon, k12 dot epsilon 3 over y12, y13, y23. No, this is y31, y32, y12. Yeah. And now, if we agree that each of these quantities is a quantity with sign, as Sunil suggested, then every cancellation is perfect. Okay, but now this 1, 2 has a 2, 1. I think that's probably going to be the rule. Okay, so that's the first kind of term. Oh, I'm going to have to go in a minute. Okay, so now the second kind of term involves a contraction of 4 psis. Okay, these two psis are not allowed to contract with each other because they're normal order. So one of these has to contract with one of this, and the other one has to contract with one of these. Okay, so we just use Wick's theorem. Okay, this is now totally straightforward, because basically what we'll get is one term will be like a k3 dot epsilon 2 and epsilon 1 dot epsilon 3. But then there will be also the other term, which is k3 dot epsilon 1 times epsilon 2 dot epsilon 1. Okay, I'm going to ask you guys to complete this. Do the contractions. Keep track of all signs carefully. Let's assume that we should look at the C ghost thing with sign. I think that's going to be the right rule. Okay, and compute this. Yeah. We'll do it properly next class. I'll also just justify it. Sorry people, sorry I got stuck on this stupid thing. Still, it's worth it because hopefully we'll understand it well.